can I? So that's okay. Yeah, I'll just try. So first of all, I'd like to thank the organizers, especially Claudia and Hasnar, for invitation. So this is my fourth time in Rio because my wife is Brazilian, and I expect to keep coming back. So I hope to keep in touch. And so I'm going to talk about stochastic control for like Levy processes. And I just realized yesterday, so we had like nice talks on this stuff. So I was quite prepared to talk about the basics, but I'm going to skip the basic a little bit. And instead, I think I can talk about like one more problem, which is about impulse control. But it's not in the abstract, but it's going to be quite a similar problem. So I think I can finish on time. Okay, so as you see, stochastic control can get quite nasty, but the kind of problems I work on is like simple ones. And what I mean by simple is that so basically the optimal solution is quite intuitive and is characterized by one or two parameters. And so basically the simplest example of stochastic control is maybe like optimal stopping. So if you think about the case of perpetual American option, and so basically what you can expect is that the optimal solution is going to be characterized by like one parameter. So basically, so it's quite intuitive that so if you think about the case of call option, if it's a perpetual, so you just maybe like set up some boundary, and then you just exercise for the first time it goes above. So it's just like that, and then you just stop right away. And so another variation of optimal stopping is like singular control, as you saw yesterday in the like definitive dividend problem where you want to maximize the total amount of dividends until the time of ruin. So in that case, so what you get is that so basically you want to use money only when you have enough money. Okay, so in that sense, maybe it's quite reasonable to do something similar. And you just set up some threshold, and you just reflect. So whenever it goes above, you just push it downward so that it's going to be a reflective process. Okay, so these are two examples where like one parameter characterizes the optimal strategy. And then what I'm going to focus on today is for the case when you need like two parameters to characterize the optimal strategy. And like one well-known problem is called like impulse control. So if you think about some modification of the singular control, and you add the constraint that so each time you activate the control, and then you have to pay some fixed cost. So in that case, so you want to act like that because so so this one just controls continuously. And if you have a fixed cost, each time you activate, you have to pay. So you want to minimize the number of control. Okay, so essentially what you get is that, so it's quite intuitive that maybe you should have like two boundaries. Okay, so what you should do is that so whenever it touches the upper boundary, you just push it down to another boundary. And then the process starts here. Like that. So you just keep doing that. And so this is typically called like SS policy. And I don't remember which one is which, but there's small s and the capital S. So basically, whenever the process goes above the capital S, you just push it down to the small s. So in that case, you need two parameters to characterize the strategy. Okay, so that's the example where you need two parameters. And the second example is it's a game between the two players. So if you think about a game, which is a zero-sum game between two players, and they share the same payoff function. So one wants to maximize and the other wants to minimize. And if each player's strategy is going to be of one parameter strategy like this, So basically, you would need like 2 parameters to characterize the equilibrium strategy. Okay, so that's a second example. And the third example is what I'm going to talk about today. So if you think about a case where you have some cost function, which is first decreasing and increasing. And the cost is going to depend on the state of the process, which basically moves like this. So you don't want the process to be too high or too low. So it's quite reasonable to set up some boundaries, 2 boundaries, let's say like A and B, such that so whenever it tries to go below the level A, you just push upward. And whenever it goes above B, you just push it downward so that it's going to be reflected at the 2 boundaries. Okay, so in this case, you need 2 parameters to characterize the optimal strategy. Okay, so that's the first thing I'm going to talk about. Okay. So let me just go back to the 1 parameter case. And so I just try to give you some intuition about like how to solve. And for some special cases, if you assume a nice property of the underlying process, then in that case, you may be lucky enough to compute the expected value for any threshold level. Okay, so to implement that, you have to specify the boundary. So let's say this is A. So for each A, so you have a strategy, and for each A, so if you fix the strategy which is parameterized by A, and you assume that the expected value can be computed by this function. Okay, so then the life is going to be quite easy. Okay, so what you essentially can do is that, okay, so first you focus on this set of strategy. Okay, so then you want to find the best one. Okay, so maybe like one quite intuitive option is to just take the derivative with respect to this level A, and choose A such that this vanishes. Okay. Okay, and another way is typically called like a smooth fit or continuous fit. So it's going to be equivalent to this first order condition. Is that so at the end, so you have to show the optimality of the strategy, so which is called the verification. So for the verification, so you have to use the Ito's formula. So in that case, so you have to choose this function B such that, so this is going to be smooth enough. Okay. But depending on the choice of A, so it's not going to be smooth enough at the level A because it's sort of pasted together, the function above A and the function below A. Okay. So what you want to do is to find A such that the function BA is going to be smooth enough at the pasting point A. So basically, you have 2 ways, smooth fit or the first order condition. But typically, you end up having the same condition. And if you assume like a spatially homogeneous process like a Levy process, what you essentially get is some function like this. So these conditions are going to be equivalent to some condition such that there's some function, let's say a gamma. Okay, so these conditions are going to be equivalent to the condition that, so this function just vanishes. So if you assume some nice payoff function, so typically if you assume some monotone function, then this function is going to be some monotone function. Okay, so you want to find A such that, so this guy that vanishes. So if it's monotone, you just want to find A such that this vanishes. Okay, so now it's going to be your candidate strategy. Okay, so then, so if you do that, so this smoothness is guaranteed already. And then, so you have to verify. So this is going to be the hardest part of the problem. But until this point, as long as you can compute this VA, then until this point, it's only like high school mathematics. So after that, maybe you need some like college mathematics to do that. Okay, so this is like 1 parameter case. And so what's going to happen if you change to the two-parameter case? Then it's not going to be too intuitive in this case. Okay. So assume again that so you can again compute this guy, so which is parameterized by lower boundary A and upper boundary B. So for each pair of A and B, so you have so imagine that you can compute this expected value. Okay, so you want to maximize B or minimize B. Okay, so why don't we just try to do the same thing as the one parameter case? Okay, so in that case, you have to identify two parameters, so A and B. So that means that you need basically two conditions. So like first, so basically you can pretty much do the same thing. Okay, so either you take the first order condition at this level A and at this level B. So then you get two equations, and so you have like two unknowns and two equations. So if you're lucky enough, then you can get some pair of solutions such that so these two first order conditions are going to be satisfied. Okay. So another way is to do the same thing as the one parameter case as well. So in the end, you want to have the smooth function. Okay, so you want to find a curve such that it's going to be smooth enough at the level A and also at the level B. And then you end up having the two same equations. Okay, so either way, so basically, so if you take the first order condition or the smoothness condition, you end up having the same two equations. And you want to find the solution to these two equations. Okay. So typically, so these two equations tend to be quite nonlinear. But the good news is that so these two equations are going to be quite related to each other. And from my experience, what you basically get is that so these two equations are going to be equivalent in that so the first equation is going to be the equation such that so there's a function gamma, big gamma. Okay, the first condition is going to be such that this big gamma that vanishes. And the second one is going to be the condition such that its partial derivative with respect to one of the arguments is going to vanish. Okay. So if you have that, so then the life is going to be much easier. Okay. So you want to find a pair of A and B such that so there's some slope which should get tangent to the x-axis at some point. Okay, so it's quite hard to see, but basically what you want to find is that so this is a plot of gamma function for fixed value of initial value A and as a function of B. Okay, so you want to find a curve such that so it starts at some positive value and goes down and gets a tangent to the x-axis at the level B. Okay, so if you can find a curve such like that, so that then the starting point is going to be your A star, and the point which touches the x-axis is going to be your B star. So then, so if you can find a curve like that, then the smoothness is going to be guaranteed. So then you can move on to the verification. So I'll just get back to that. Okay, so objective of this first part of the talk is to basically work on this problem. So you have some, you know, like a convex-looking cost function, and you want to find the best strategy so as to minimize the sum of the running cost function, and also the controlling function. Okay. So basically, you want to so you don't want the process to be too high or too low, but so you want to push it, push into some interval. But to do that, you have some cost. Okay. So the cost is going to be like this form. Okay. So this process U is going to push the process upward. So this is U, and so this is going to be D. Okay. And we assume that the cost is going to be proportional to the amount of control. And the unit cost of pushing it upward is going to be Cu. And the unit cost of pushing downward is going to be the CD. So these are some constants. Okay, so you just want to sum up these running cost and the controlling cost. And you want to find the best strategy such that this is going to be minimized. So you want to find a pair of processes U and D such that so this is minimized. So this has been studied like a long time ago. And so Agnes Lim, I think I was expecting her to be here, but maybe she canceled. Okay, so she worked on the case of a Brownian motion for the case when the process X is a Brownian motion. And what I'm going to talk about today is to think about a case when X is a Levy process. Okay. So what I'm going to do is that first I'm going to talk about some basics about like Levy processes and fluctuation theory, but you actually have seen already yesterday. So I'll just go quickly about that. Okay, after that, so we can just basically pursue this classical like guess and verify strategy. So which means that you first guess a solution and then verify that so this is indeed optimal. And the guessing part is basically this one. So you want to identify the pair of A and B. Okay, so that the process is going to be going to stay in this interval. So after that, it's a verification argument. And so if I have time, so I'm going to talk about another problem, which is like impulse control problem. So which is like one-sided, but you have so you sort of have this one. So in this case, 2. So you have like 2 parameters to characterize the optimal strategy. Okay, so these problems are quite similar. Okay, so let me so model the problem. Okay, so we are assuming that so there exists like speculative negative Levy process, which is again the Levy process with only negative jumps. And so this is going to be X. And what we want to find is a best strategy. And each admissible strategy is a pair of a process U and D, such that this process U that pushes upward, and the process D pushes the process downward. Okay, so these are assumed to be Kazlag and adaptive process. And we assume that so this is going to be finite, so that so this expectation makes sense. Okay, so about this running cost function f. So we are basically assuming that it's going to be some convex function. And okay, so about like Cu and Cd. Okay, so again, so Cu is the cost of pushing upward, and Cd is the cost of pushing downward. And so these actually can be negative, so it can be a reward to push upward, downward, but you have to assume that so if you sum up, so it has to be positive. Because otherwise, so if it's basically negative, so basically then you can just cheat by activating pushing upward and downward a lot of time, then you can get the infinite amount of reward. Okay, so we assume that if you sum up these two costs, it has to be positive. Okay, and also, so X can have a, so depending on the Levy measure, so it can have a infinite moment, but we have to assume that this has a finite moment. Okay, so about F again. So basically, the key assumption is that it's a convex function. So it has to be convex. And for technical reasons, so we don't want this function f to grow too rapidly. And maybe this is not necessary, but we just assume here that it has have a polynomial growth at the tail. So this is sort of needed because at the verification argument, so you have to use the Ito's formula. So to do that, so you first localize and take the limit saying, and in order to exchange the limits, so you need so this property. Okay, so this is sort of minor assumption, but if you just tilt this function by this cost like CU, and it has to be first decreasing and increasing. Okay, but just try to imagine that the function is to have has this form. Okay, so you have seen this yesterday. So I will just try to go quickly. But so the best way to characterize, way to start about the Levy process is by Laplace exponent. So which is basically that. So if you take the Laplace transform of the Levy process at time 1, and if you take the log, so this is called the Laplace exponent. And so this can have this decomposition. And so basically you can see the property of the Levy process by this form. Okay, so middle term is called like diffusion term. So this is about the Brownian motion of the process. And so this is about the jump term. Okay, so nu is called the Levy measure. And the Levy measure can blow up around 0. But if you take the second moment, it has to be finite. Okay, so and this is sort of the remaining term. Okay, so and in the stochastic control, so this is kind of quite important. It has a lot to do with the smoothness of the value function. Okay, so the process has path of a boundary variation if and only if there's no Brownian motion. And also, if you take the first moment of Levy measure around 0, it's going to be finite. Okay, so if these are satisfied, then the process X has paths of boundary variation almost surely. So otherwise, it's going to have paths of unbounded variation almost surely. Okay, so these are going to be quite important. And we also have to exclude the case that X is a subordinator, meaning that X cannot have monotone paths almost surely. Okay. Okay, so we assume the expected negative Levy process for X. And again, so you have seen this before. It's about scale function. Okay, so scale function is going to be quite useful. And so this exists for every expected negative Levy process. And it's characterized by its Laplace exponent. Okay, so let's say this Q is a discount factor. I mean, it doesn't have to be positive. It can be 0 or negative. But here, we assume that the discount is positive. So let's say Q is positive. Okay, so this function is a mapping from a real number to positive real number. And so basically, it's 0 on the negative half-line. And on the positive half-line, it is going to be defined by the Laplace transform. So if you take the Laplace transform, so it's going to be 1 divided by the Laplace exponent minus the discount factor. And this holds for every s which is bigger than this phi. And the phi is going to be the largest solution to the equality that the Laplace exponent equals q. So the Laplace exponent on the positive half-line for the expected negative case is always convex. So either it has so this form, or just like monotonically increasing. Okay. So this is for the case when the process drifts to minus infinity. So this is for the case, and this is for the case. Okay. And so basically, this capital phi is going to be, so if you just set up q, so this is going to be phi. Okay, same for q. And the scale function is going to be basically, so this scale function typically has this form. So basically, it's it's 0 on the negative half-line. And depending on the path variation, okay, so for the case of unbounded variation, so in that case, it's continuous at 0. And then it just grows exponentially. But for the case of boundary variation. The key difference is that so it's 0 on the negative half line again. But at 0, it's going to be not continuous. So it's going to start to some value and like this. Okay, so these two differences are going to be quite important in this stochastic control problem. Okay. So this is about scale function. So it can do so many things. And so the most basic thing is about the two-sided exit. So if you define tau A minus to be the first time the process goes below A, and tau B plus to be the first time it goes above B. And then if you think about the scenario where it goes above B before going below 0, and if you think about sort of the discounted version of the probability, then it can be written as a fraction of the scale function, like this way. And you can also say for the other event that the discounted version of the probability that it goes below 0 before going above B can be written in terms of this form. And Z is, again, appears quite a lot. It's again called a scale function again, second scale function, which is going to be like 1 plus the discount factor Q times the integral of W. Okay, so these quantities can be written in terms of the scale function quite nicely. Okay, so there's so many things you can do with a scale function, but I'll just skip about this. And so basically, using a scale function, you can obtain some identities for this process. Okay, so let's just go back to the strategy such that so you just reflect the process at the lower boundary A and upper boundary B. Okay, so this is a feasible strategy. And let's say, so let's name this guy as UTAB and DTAB. So UTAB is going to push the process upward so that the process is not going to go below A. And DTAB is a process that pushes downward so that the process is not going to go above B. Okay, so if you just sum up, okay, X plus U minus D is going to be the process which is called like doubly reflected process, okay, which stays on this interval all the time. Okay, so this had been studied a while ago, like maybe 10 years ago, by Martin Pistorius in Imperial College. So basically, he obtained like fluctuation identities for this process, and so we can just basically use what he used. Okay, so now you have a very good start. So what we have is this one. Okay, so you can replace a y by YAB for the case of a doubly reflected process. So this is called like potential or resolvent. So this can be computed using a scale function. And also for this, so discounted sum of control can be also written using a scale function. Okay, so if you just sum up, so you have the corresponding cost for the doubly reflected Levy process. Okay. Okay, so if you sum up, basically everything can be written in terms of scale function. So, okay, so it's quite ugly, but so I'm not cheating at all in that so everything is defined well. Okay. So here, so I define W and Z. So how much time do I have left? Until 40? 20 minutes. Okay. So W and Z. So R is going to be another function. Okay, so Z bar is another integral of Z plus the first moment divided by a discount factor Q. Okay, so this gamma I'm going to define later, and which is going to be an important function here. Okay, so expected value is going to be written in terms of this form. If the starting point is below B, okay, above B is going to be just so this guy. Okay, so what you expect is that basically expect some function like this. And so this is going to be linear because you just pushed upward, and it's going to be linear because you just push it downward. Okay, so the slope is going to be CD, and the slope is going to be minus CU. Okay, but depending on how you choose A and B, the function V. Okay, so this is V AB. So it may not be smooth enough at the level A and B. Okay, so what we want to do is to find a pair of A and B such that this is going to be smooth enough at the two levels. Okay, so that's what we're going to do. Okay, so here, this big gamma function is defined by this way. Okay, so this is written in terms of the scale function. Okay, so W, Z, unit cost of pushing up and downward, and another integral derivative of the scale function. Okay. Okay, so now, okay, because you have this guy, okay, and you just want to find the smoothness of A and B, so you can just differentiate this function VAB to obtain A and B such that it's going to be smooth enough at the level A and B. Okay. Okay, so it's quite straightforward. So it's just like high school mathematics. So what you basically get is that, so if you take the first derivative and think about the point B, and in that case, no matter what, so it's going to be first differentiable all the time. Okay, so you get no information about this. But if you think about the first differentiability at the level A, okay, so then what you get is this one. Okay, so for this to be smooth, the first differentiable at this level, so this has to be like minus CU in that, which means that so this guy has to vanish. Okay, so now let me just go back to the plot of the scale function. Okay, so again, so at the point 0, for the case of an unbounded variation, so W0 is always 0. Okay, so in that case, so this vanishes all the time for the case of an unbounded variation. Okay, so this holds for all the time for the unbounded variation case. But for the case of a bounded variation, so this is not 0. Okay, so for the smooth fit to hold, so basically, so you have to choose A and B such that this guy vanishes. Okay, so then you get like more information. Okay. Okay, but that's not enough, so why don't we just proceed to a second derivative? Okay, so if you take another derivative and think about that twice the differentiability. Okay, at the level B, okay, so if you take a second derivative, so it's going to have this form. And for this to be twice differentiable here, because this is linear, so you just want this to vanish. Okay. For the case of unbounded variation, you have chosen AB such that so this guy vanishes, so this one vanishes. Now we have extra condition that so this function, which is a partial derivative of the function gamma, is going to vanish. Okay. For the case of unbounded variation, okay, so at this point you have no information at this point. So in that case, you think about the second derivative at the level A. So in that case, again, for the case of unbounded variation, so W0 is 0. Okay, so but you want to find, so this has to vanish, so you have to choose AB such that this gamma is going to vanish. Okay, and then go back to this one. Okay, so this has to vanish and this has to vanish again. Okay, so in conclusion, what you have to do is to find a pair on A and B such that so this big gamma and small gamma, which is a partial derivative of this guy, vanish at the same time. Okay, so in that case, what you get is some smooth function, which is going to be, for the case of a bounded variation, it's going to be differentiable at the lower level A, at the lower level A and twice differentiable for at the upper level B. Okay? For the case of unbounded variation, it's going to be twice differentiable at both boundaries. Okay. Okay, so that's smooth enough to apply the Ito's formula. Okay. So now also we sort of have to show the existence of a pair of A and B such that so these two functions vanish at the same time. Okay, it's quite ugly because the scale function doesn't have a nice form either. Okay, but the good news is that so these two equations are not totally independent. In that the second guy is the partial derivative of this guy. Okay, so again, I'm just going to show you this plot. Okay, so this is a plot of gamma for fixed value of A, and as a function of B. Okay, so what you want to find is basically that you want to find a curve such that it starts at A, goes down, and gets tangent to the x-axis and goes up. Okay. So to show that, so basically you can say something like this. So if you take initial value A, like large enough, then you can show that it starts at the positive value and just monotonically increasing. But if you just pull the initial value A downward, what you get is that it just tends to decrease. And eventually you have to get a curve such that it gets tangent to the x-axis as it goes up. Okay. So in this case, the starting point, so the red curve is what you want. And your A star is going to be the starting point of this red curve. And the B star is going to be the point where it touches the x-axis. Okay, so that's going to be your strategy. Okay, so you choose A star and B star like that. So if you choose like that, so it's going to be smooth at the level A and the level B. Okay. Okay, so I'll just skip that. Okay, so if you choose that way, so actually the candidate strategy, so VAB is going to be quite simplified. So this is what you got, so, but you have chosen A and B such that this vanishes, so you don't have this term anymore. Okay, so now we have simpler term. Okay, so now, okay, until this point, the life is quite easy, but from now you actually have to verify the optimality. Okay, so what you have to do is basically this one, the variation inequality. Okay, so it just requires that, so first, so there's a condition on the slope of the curve, okay? So which is basically says that the slope is going to be bounded between minus C and CD. But it's kind of clear from this plot in that, so below A it's linear, and the slope is minus CU. And above CB, the slope is going to be CD. Okay, so you can also have this smoothness at the level A and B, and then you can also show that it's going to be convex between A and B. Okay, so that's going to show the first one. Okay, so it's not going to be too difficult. So after that, okay, so you need about this operator thing. So if you take the generator, so let's say like L is a generator of the process X. So what you have to show is that so it's going to be harmonic between A and B where you do nothing. Okay, but if you whenever you activate above B and below A, so it has to be a superharmonic. Okay. So, so I'm not going to go into the detail, but basically 3 and 4 should be quite easy because between A and B, because you do nothing, so it's basically you can use some martingale property. Okay, so it's quite immediate. And below A, so it's not going to be quite difficult because it's just like a linear function. And remember that the process X only jumps downward. So if you're here, it just jumps downward, so it just stays in this linear region. Okay. Okay, so in that case, it's quite simple. And the hardest part is going to be like number 2. Okay, so which is going to be like 5-page proof. So I'm not going to talk about that. But basically, if you're here, so what's going to happen is that it may just jump downward. So so there's basically 3 regions. And it can go from activating region to this waiting region. And it can even jump to another activation region. Okay. So because of this, so this number 2 is going to be the hardest part of the proof. But so I'm not going to touch it, but so this is basically the hardest part of the paper. Okay, I'm not going to talk about this. Okay, so I will just show you some numerical results. And here, I use about this like metamorphic Levy process. So which is sort of extension of hyper-exponential Levy process, which means that so jumps are compound Poisson. And so it's a linear combination of exponential jumps with different parameters. But metamorphic Levy process is going to be some extension of that, in that so you have like infinite number of options for the exponential parameters. Okay, so basically what's good is that so if you just focus on this Levy process, then the Laplace exponent phi is going to be like a rational function. Okay, so remember that the scale function is defined by its Laplace transform. So if you take the Laplace transform, it's going to be written by this Laplace exponent. Okay, so in this case, you can just analytically invert it to obtain very nice form of scale function. Okay, so for the numerical results, I'm going to focus on this beta family. So which is basically the Laplace exponent is written using the beta functions. Okay, so this is actually a nice process in that so it has this property, and also it can approximate temper stable process like a CGMI process, which is quite used in finance. Okay, so I'll just show you some 2 cases. Okay, the first case is when this so function, cost function is quadratic. Okay, so in that case, you basically see no surprise. Okay, so everything works quite nicely, and so this is how so this is how the Bali function looks like. So there are like 2 boundaries. It's maybe hard to see, but there are 2 triangles. This upper triangles and lower triangle. And so you just push upward whenever the process goes below this triangle. And same for this guy. Okay, so this is plots for many values of CU, and this is a plot for many values of CD. Okay, so what's interesting is the linear case. So if you think about the absolute value of the state, then because obviously, so this is not going to be smooth at the point 0, so you get some ugly things. So in that case, so what you can see is that basically if it's linear, so it can happen that the B star can be infinity. Okay, so because the cost is not gonna go rapidly, so if the cost of pushing downward is too big, so then so there will be no motivation to push the process downward. So it can happen for the case of a linear case, but it won't happen for the quadratic case. Okay, so I have 5 minutes, and so I will just go quickly about the difference between what I just talked about and this impulse control problem. Okay, so it's quite similar problem. Okay, so in the impulse control problem, okay, so we just focus on the case of a one-sided case. Okay, so basically, so you have similar cost function, but you can just only push it upward. Okay, so otherwise I don't know how to solve. Okay, so then So the main difference is that, so basically we add the fixed cost in that each time you activate, so you have to pay some cost, okay? So you don't want to just reflect because you don't want to activate that many times. Okay, so in that case, so you can just sort of imagine that some like SS policy is going to be optimal in that, so you set up some small s and capital S, and then whenever the process goes below S, you just push it up to capital S. Okay, so now, so in order to characterize, so you need to choose like two parameters, small s and capital S. So this is a classical problem of an impulse control problem. Okay, so we basically assume the same thing for the cost function and the underlying process, x. And so it has been shown, people like Ben Susan have been working on this problem. And typically they worked on the case of a compound boson with or without Brownian motion. Okay. But it turned out that so if you use this technique, it gets much more simple. Okay. So you don't have to take care of ugly, differential equations and so on. Okay. So basically, so you can solve that. Okay. You basically assume the same thing for the function. And so you basically, what you want to do is to again minimize the sum of cost function and also the controlling cost. But in this case, it's going to be different in that, so each time you control, you have to pay some fixed cost. Okay, so that's the only difference. Okay, so basically, so everything can be written in terms of scale function again. Okay, so you have the expected value corresponding to this strategy, the SS policy. And then, so what you have to do is that, so you have to choose the value of S and S. And again, so you need two conditions, two equations to obtain a pair. And what you basically do is to, so about this small s, so it's going to be quite clear. So you want to find S such that it's going to be smooth enough at the level S. But you have nothing about this one. But typically, what you should do is that you're going to choose the level S such that the slope of the value function at this level is going to be the same as the proportional cost. Okay, yeah, so I should just go quickly. Okay, so basically that's it. And so you basically get two equations. Basically, you get two equations, and if you're lucky, you can obtain a unique pair of a solution to these two equations. Okay, so I think everything else should be the same, and you basically get the same graphical interpretation for the existence of a pair of S and S, and so on. Okay, so yeah, we should go to excursion, so I should stop here. Okay, so I just talked about two things. The first part is about a two-sided control. So this is actually the joint work with Eric Bardot from London School of Economics. And the second one is, so this is about the SS policy. Okay, so thank you for your attention.